Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the title that I published earlier was Scaling Up Extraction and Search Over Entities, but I'm going to restrict myself more or less on the topic of extraction and motivate the problem with search. So I'll motivate this problem with the problem of search. So imagine a query of the sort, professors who were keynote speakers at conference. This is fired on Google, and all we get is a bunch of URLs. We really don't get the names of those profs and the names of those conferences. But imagine you were looking for a list popping up on the first result page. Or there's another query, people from computer science and electrical engineering department who have collaborated on a project. Well, let's say this is focused on a particular university. So what you're seeking here are instances of types. You can call them entities. And you're also looking for relationship between entities. So more examples. You could have entity queries like find experts on databases or related to Microsoft. Or you could have an entity relationship query, which is IIT Bombay alumni who founded companies related to search. So when we talk about entities, we're basically talking about some annotations. And we'll go over an overview of what kind of annotations are possible. By no means is that meant to be exhaustive. So we start with information extraction, and it is well known as a problem of dynamically extracting instances of a type system. Ontology population, the ontology in a very broad sense gives us a type system, and ontology population is about attaching entities to the ontology. The third problem of entity disambiguation is finding spots in text and associating them with entities in the ontology. And I'm going to abuse the word ontology. By ontology I mean word, I mean Yago, I mean Wikipedia. I also mean formal ontologies. In the process, we would also like to discover and leverage structure between entities. This is something that I haven't done, but I have basically just leveraged. So for example, you might want to realize that Einstein is a person, Einstein is a scientist, and so on. So most of the work is about the work I'm going to present is about making use of these relationships rather than discovering them. So this is the formal definition of an ontology: the set of representational primitives with which to model a domain of knowledge or discourse. The representational primitives are typically classes, attributes, and relationships. Some people believe that ontologies are by design always domain specific. So I will be talking about two quote unquote ontologies. One is a domain specific ontology which we have developed for the academic domain, and the other is Yago augmented with Wikipedia. So let's look at the range of annotations we just talked about. On the left hand side, what you see is an ontology with some nodes, with types, and with instances, all in the same color, and with edges denoting an is-a kind of relationship. So person is a thing, location is a thing, scientist is a person, state is a location, Washington US state is an instance of state, and so on. So an example of this is Yago, which is a directed acyclic graph. It has approximately 2 million entities. By entities we mean the leaf level nodes here. These are entities, and it has close to 0.24 million types. And it has 96 relations like author of, director of, etc. And here on the right hand side is a small passage. This is a snippet of text. The southernmost border of Washington follows the Snake River. So this is supposed to highlight Snake River. So this Washington is potentially a location associated with this ontology. It could also mean one of these more specific Washingtons in the ontology. Again, snake could be very generally associated with location, or more specifically with one of these entities in the ontology. So information extraction we define to be the problem of attaching word sequences in text, or spans in text, more formally spans with nodes in the type system, but more specifically higher level nodes in the type system. The second problem of ontology population is, given a large collection, which I haven't shown here, but given a large collection, identify and associate spans with nodes, the types in the ontology. So you might have Washington DC occurring a bunch of times, Washington US state, and the problem is to identify that this is basically a city, this is a state, and so on. Yes. So by type system being static, you mean the top level? Yes, for the purpose of this, purpose of our work, we assumed it's static, but there has been work on dynamically discovering nodes in the type system as well. I must say that keeping everything dynamic is quite tough, so you need to decide what you need to hold static. So we decided to hold the type system static. And the third problem of entity disambiguation is associating spans in the text with more specific nodes in the ontology, in this case the leaf level nodes. We also use some of the techniques I'm going to present to build an academic ontology at IIT Bombay, much smaller than Yago, has around 50,000 instances, 200 classes. By classes I mean types. There's 50,000 instances were dynamically populated. The classes were all frozen. And we built on an existing small academic ontology. This was presented at the Semantic Web conference this year. And a lot of our work is also motivated by vertical search systems as against generic web search engines. And these vertical search systems are typically characterized by an input query, query processing. Now the query processing basically will, this web, it can also be an input to the query, to the search system. However, the focus is more on the homegrown corpus, the enterprise corpus, so to speak, which is indexed, and this index is accessed by the query processing and ranking module. Now, what is more important in the work we are doing is that this index is highly enhanced with annotations. Some of the annotations I talked about, and these annotations all refer to the ontology, a populated ontology. And the idea is that this populated ontology can be also populated further using this corpus. So while the populated ontology serves a input query, it is itself populated using the corpus, which is trying to which it refers to at runtime. Yeah, so this ontology could be replaced by some larger internet encyclopedia like Wikipedia. And what kind of queries are we talking about here? So imagine that you are interested in instances of physicists, where physicist is a node in Yago. You are in additional interested in selectors. Selectors are words that you insist a result, a return snippet should contain. A query can also consist of multiple contexts. So the context could consist of selectors, context could also consist of other entity types. And in addition, you might insist that you need an ordering between the entity types or the instances. You need some proximate weight between them and some window width constraints. So here are examples. To find the lead actor in the Mission Impossible movies, so you're looking at an unordered window, you're looking for the type actor, and within 50 characters, you're looking for, well, here it's characters, 50 characters, looking for these selectors, the 3 words: mission, impossible, and lead. Slightly more complex query, you're looking for an unordered window of types, 2 types, type 1 which is scientist and type 2 which is a musical instrument, and the intention is to get a table of scientists who play certain musical instruments. And a third example is to find American feminist that appears on a silver dollar. So here again you're looking at a single type, but what you're looking for is a phrase selector. So silver dollar, you insist that should occur in a vicinity of 30 characters around an instance of the American feminist type. So how do we handle such queries? Well, as I said, we are going to assume that there are a bunch of annotators, the 3 levels of annotations that we have subjected the corpus to, and we'll briefly concern ourselves with, well, how do you put all this into the index so that we can efficiently answer such structured queries. So there are a bunch of existing indexing mechanisms. There's a shallow semantic queries and entity rank and lemur. Lemur is a well-known off-the-shelf indexing engine. However, we found that the memory footprint that these indexing engines incur is actually quite prohibitive. So basically, the excess footprint you incur because of entity annotation could be as bad as 10 times or 50 times the size of the original index. So we set out investigating how we could compress the index and make it possible to hold it in memory and also efficiently answer such structured queries. We did some experiments with the Yago ontology in this case. We made use of a cluster of 20 machines, 500 million web pages from ClueWeb. So there was also some redundancy in the indices that we stored. So how do you go from annotations to indexing? First of all, we assume that entity labels or types have been associated with a sequence of tokens. In addition, we are also allowed to associate uncertainty measures with the association between the spans and nodes in the ontology. It's important to index the context around an entity type. So basically this entire index we have for the entities is about storing the context around entities. So collect context around a mention and create context word backs for each entity. That is the key. Now you could have ambiguity here. For example, it might not be possible to zero down on one of these entities for Washington. So you might want to retain multiple associations. That's also possible, along with the uncertainty score. So we built this interleaving of snippets and posting lists index, abbreviated as SIP, and it's actually very modular and easy to extend. It was built using MG4J, and there were basically 2 types of indices. One was the index for the text tokens, the ordinary index, and the other is for entities and types. This will be described in the next slide. So ordinarily a posting list consists of a mapping from a span in the text to all the positions it occurs in. So if you have Washington as an example, you'll have all the documents and the offsets in those documents that Washington occurs. However, SIP has an additional index, as I mentioned earlier, which is a mapping from types. So this entire list you see here is for a particular type. This type could be city. For each type, the documents in which it occurs, and then all the entities under that type that occur in this document. So unlike some of the other indices which actually maintain a list or a postings list for each entity, we maintain a posting list for each type, and that helps us tremendously in terms of saving on our memory footprint. In fact, these entities are not stored as they are. These entities are mapped to dictionary IDs, and what we store for multiple occurrences of these entities in the document are their offsets. In addition, the document IDs are gamma encoded. There is also some encoding that we use on the entity dictionary IDs. So given an input query, the input query, as you saw, has a predicate ordered, unordered, followed by the types, some optional argument, the number of characters, and selectors. So all this is basically represented in the form of something called an abstract syntax tree. It's a tree, and so the query parser creates an abstract syntax tree, and this abstract syntax tree is used to look up into this index. So this decorator is basically just going to decorate nodes in this tree with posting lists in the index, as you see here, the text index and the zip index, and the rest, whatever follows, is basically just filtering on these indices. I'll give some more details of what kind of filtering goes on when I talk about scaling up the entity extraction process. So yeah, just as a context, basically this helped us tremendously in terms of reducing the size of the index itself. So SSQ is one of the existing best indexing mechanisms or systems. So our total index structure, as you can see, is less than 1/40th the size of the SSQ index. And we also compared for different densities of the annotations. So you could have annotations, one annotation every 5 tokens, one annotation every 20 tokens, and we observe the effect of the density, and we find that we scale pretty well. Okay, so this was basically the context that, well, search over entities is possible using interesting index structures. What I'll present for the rest of my in the rest of my talk is that these same index structures, well, slight variants of these index structures, could be used to create the information extraction database with orders of magnitude speed up. So I just recall the 3 phases: information extraction for simple type system, this is at the top, then entity disambiguation, and ontology population. These were the 3 problems, and we'll talk about scaling issues in each of these and algorithms and approaches that could help us achieve the scalability. Yes, yes, please.
How is the structure of this learned actually? So this thing, the hierarchy here. How is exactly the hierarchy learned?
How is this hierarchy learned? Well, we haven't done any learning on that, and as far as I'm aware, there isn't there has been much success in learning the hierarchy as such. People have tried. So generally, what people have restricted themselves to is assuming this top level and just attaching the leaf nodes. Now there is some work on completing ontologies. So imagine you have some nodes here and you want to attach some additional nodes. So there's some work on that, bootstrapping. But learning from scratch, people have tried, but I'm not impressed. Not queries. Mm-hmm. Okay, so let me answer the second question first. So as far as temporal information is concerned, if you have the information already extracted on the documents, that's not very difficult. In fact, even off-the-shelf search engines like Lucene allow you to do some date range queries. Now coming back to the first question, not queries. While we haven't really implemented, I would imagine it's very easy because most of our Operations are operations of intersections and unions, and we could easily have subtraction on the posting list. So we haven't handled because we didn't see a case, but yes, I think that should be easy to handle.
So is Yago just one of many different kinds of tags in the community, or it's important for some reason like being the biggest?
So in fact, some of the guys working at Yahoo might have better experience, but my experience shows that Yago is one of the cleanest category hierarchies. We have tried working with Wikipedia and DBpedia, and on one hand, Wikipedia has too much of noise, absolutely meaningless paths in the DAG. On the other hand, Freebase also has a type system, but the type system in Freebase is somewhat restricted to people and music. Yeah, so it's a small type system, a smaller type system. Pardon? No. So, in fact, yes, my student did look at the healthcare ontology in this year's semantic web conference paper, but our work is not as exhaustive as we have done with Yago and the academic ontology. Any other question? So, another question that pops up is, let's say we want to do these annotations, all the 3 levels. How do you go about them? Do you start from the top and then build annotators going down, or do you do some bottom-up construction of annotators? After a lot of investigation, this was just a design choice. We decided to go top-down, build annotators for types, the abstract types, and then do ontology population, and then look at the problem of entity disambiguation. So we go in that order. So information extraction for simple type systems. So this is the again a formal definition. Given a schema, you want to extract all instances of that schema. So we're going to, for the sake of this problem, we're going to ignore the hierarchical structure because we just given the types, and often we're given a schema and want instances of the schema. Here's an example. You're interested in people, name of a person, his title, and the organization. So Bill Gates is the CEO, or was the CEO of Microsoft, and so on. So the old information extraction school has been primarily driven by rule-based approaches. And as one of the speakers in the morning subscribed to the old school of thought, I'll do the same here. So they're characterized by the message understanding conference. There were several classic information extraction tasks, and in that process, several rule-based information extraction systems were built. So we focused on rule-based information extraction for 2 reasons. One is, even if you were to come up with machine learning-based extractors, they eventually land up using rules as features, or features which are constructed manually. So you could always interpret these rules as features. And part of the inference is feature computation, and what you're going to be interested in is learning those features and performing inference with those features or rules. So it doesn't matter too much, but yes, there are interesting research problems, as we'll see. The second reason is, in several applications, explainability is important, especially at the top level. So you would like explanation on why a particular information was extracted. So here's the anatomy of a rule-based information extractor. So imagine this document. We met Miss Anna Smith from Melinda Gates Foundation. So the first thing you do is identify some basic features, regular expression patterns, dictionary matches. So first name dictionary match, last name dictionary match, and capitalization, 3 example features. So these we refer to as basic features. At times we call them rules, basic rules. The second is candidate definitions. So these are candidate instances of the type system. So here's person names, person candidate with salutation, and person candidate. These are 2 distinct candidates because they have 2 different signatures. and the signatures are obtained from, say, sequences of the basic features. You can write these in first order logic. We can write these rules in first order logic. But what typically a system, rule-based information extraction system does is uses a subset of first order logic to write these rules, primarily because of computational reasons. You like to make the inference as tractable as possible. The next phase is candidate refinement. So you realize that, well, Melinda Gates was a person candidate, but Melinda Gates Foundation should have precedence. So so assume that you had an organization candidate rule, which I didn't show here. But imagine that Melinda Gates Foundation qualified for another candidate definition rule. So you would do some refinement, and the refinement here would amount to some kind of subtraction. And then you could have consolidations, which are putting together shorter spans and getting longer spans, typically within the same type, in this case the person type. So an example of such a system is system T from IBM Almaden Research Center, which I was a part of several years back. So there are other rule-based systems, and they use this is well-known language called Common Pattern Specification Language, which was adopted in the text processing system called GATE, General Architecture for Text Engineering. It is possible to write the kind of rules I hinted to in the last slide using GATE, and it's in fact its engine is called the Java Annotation Pattern Engine. Yes.
Question on rules, because rules is such a heavily overused word in language research. So you said first order logic rules or production system rules. Which kinds of rules are these?
So you could write these in first order logic, all of them in first order logic, but typically a system like system text has its own rule language because it would like to, because the language is actually a subset of first order logic. It's not the complete first order logic. So you could use existing theorem provers and prolog and then write these as first order rules, but you can be a lot more efficient by understanding the restricted subset of language that is needed and write custom theorem provers, inference engines. So that's what system T did. They're okay. So the dominant paradigm for processing using these rules or features, whatever you like, is to take the document collection, take a single document at a time, subject it to all these processings, tokenization, part of speech lookup, and then do this feature collection and do instance extraction for this one single document. You get this annotated document, and you can push this annotated document to your favorite entity index. It could be the SIP index or whatever else you like. So what would this rule do? So let's look at an example of a rule which identifies some of these instances, which are instances of organization, BP, Marsh, PLC. So typically this rule will, a rule will consist of context, and within the context a sequence of tokens, and within, for each token, a bunch of properties. You could also, so you could look at this, this particular candidate definition rule, so to speak, as a regular expression, over some basic features. So the basic features are regular expression features on tokens, then dictionary, and also some of these clean operations. So here you have comma as optional. Some of these tokens could repeat multiple times. So since we divided our entity extraction rule into 4 phases, we are taking the liberty of assuming that the first phase is done, which is, well, you have all these basic features provided to you, and you need to process an input sequence of tokens using this regular expression over an alphabet which is given by basic features on the tokens. So what is the problem with this dominant approach which I pointed out in this slide, which takes one document at a time, processes it using those rules, and creates an index or adds to the index?
So is it possible for any of these to lead to multiple annotations? I mean, from this
Overlapping annotations?
yeah.
Yes, certainly.
The scenario that you mentioned using these first order logic rules.
Yeah, I would request you to forget the first order part. You can potentially represent them in first order logic, all of them in as monolithic set of first order logic rules, but it's preferred to break up the 4 into 4 different phases and have different inference engines for each of them. So what is the problem with that approach on large corpora? So one thing you realize is a dictionary lookup on the same token occurs as many times as the occurrence of that token. So if you have PLC, as in the previous example, you look up the organization clue dictionary, and you need to do that lookup and processing thereafter on that token as many times as it occurs. So there's some repeated computation of dictionary lookups, repeated regular expression matches, and there are also large overheads when you change dictionary entries slightly. So suppose I make a slight change to a dictionary entry, I'll need to do the entire processing on the document collection all over from scratch.
This repeated lookup, is this just happens to be the case that system T is broken in this way, or it's a fundamental characteristic of rule processing as we described it?
Okay, so what I'm hinting to is that the repeated occurrences of these token, the token and token sequences are already captured through indices, index structures. So perhaps system T could be smarter and take care of repeated occurrences within a document, but what about across documents? There are also overheads when you make slight modifications in rules. You drop one of the alphabets or drop one entry in the regular expression, and also if you make incremental annotation updates by adding new rules which are slight extensions of existing rules. And whatever I'm referring to as rules here, you could interpret them as features. So this is where we are heading towards, making use of the sophisticated index for entity annotation. So this is our idea. Take the document collection, create it as inverted index, and the two parts I spoke about, generating basic features and generating the end entity, identifying entity type instances, you can break them up as two phases of lookup and operations on the inverted index. So the first phase looks at the inverted index. It's a very simple idea. You can do part of speech tag lookup, dictionary lookups, etc. on entries in the inverted index. You can't do part of speech disambiguation, only lookups. The second phase is what is somewhat non-trivial, translating the regular expression matches over token sequences to operations on the inverted index, so that what you get finally is your favorite annotation index. So what we find is simply by doing this kind of translation, we get at least an order of magnitude speed up. And there are now, once we are in this space, we are in the space of query optimization. You can do, the moment you look at regular expressions as queries on the index, you can look at query optimizing for single query, optimizing for multiple queries, and so on. So opens up a whole new gamut of problems. So
you're not using the Duke MapReduce overall control flow to do this?
No. So yes, so I have little or no experience with distributed computing, and while some of this work is old work, I was trying to find what kind of work I've done would best suit this workshop. So this is what I thought. Well, because this should be amenable to map reduce and distributed computing, but I haven't explored. So the structure of the index, just recap, you have these tokens, and for each token you have a posting list. The sorted posting list has the occurrence of that posting list, occurrence of the first token and the last token. This is basically the span in each document. Well, it could be document ID followed by sentence ID. Here I just use sentence ID. So the IDs could be adapted to whatever suits your need. Now here's a simple addition. All you need to do is look at these entries, do dictionary and regular expression lookups on these tokens, and you can easily generate your posting list for these basic features. And now to do anything more, you need to define some operations on the posting list. So merge takes two posting lists, L and L prime, assumed to be sorted, and it returns a sorted posting list where each entry in the returned posting list occurs either in L or in L prime. So the order is L plus L prime, the size of sum of the sizes. The second is cons int, which is consecutive intersection, and it basically returns a span which starts in L and ends in L prime without any gaps. Well, you can also add in gaps, and you can add additional parameters saying the gap should not be more than this or less than this. So I'm just giving you the simplest version of this implementation, but we have taken care of more sophisticated requirements. And this can be done in time depending on the size of the posting list. And finally is parallel intersection, which is looking for a span which occurs in both the posting lists. So yeah, so there are several extensions. In the interest of time, I'll just illustrate with an example. So imagine you had this simple regular expression B or A followed by C or B plus plus. So the way we interpret this regular expression, which is for us regular expression over tokens and token attributes, we convert this into a plan, an execution plan. We call it an AND OR graph, and we have some notation. So OR nodes are denoted by square, and AND nodes are in circle. So this says that A AND followed by multiple instances of this part. Sorry, B AND multiple instances of this, B or multiple instances of this part, and this part, this subtree is basically a sequence of A followed by B or C. Okay. And the idea is you take the posting list for A, C and B and pass them up, and as you pass them up, subject these posting lists to operations of merge and consecutive intersection and so on. Taking care of these plus and star operators is fairly straightforward. And this is basically the idea. So for each node V in the reverse topological sorting of this tree, you basically look at the type of the node and apply the operation corresponding to that type on the posting list coming from its children. Yeah. So worst case complexity is basically the order of the product of lengths of all posting lists, but in practice we never reach this. In our papers we have analyzed this in more detail. In the interest of time, I just present the results. So on two corpora on which entity annotations had been defined, we just subjected them to a bunch of rules, and we found that we obtained a speed up factor up to 13.26 and we also tried incremental annotations, adding new rules, and tried to look at the speed up. What happens is when we have new rules, we don't have to go through the entire pipeline again. So some of the intermediate posting lists are already generated, which can be reused. So we get better speed up. And as expected, our speed up is basically sublinear, whereas documented time is going to be linear. Now there are many interesting problems here. So for a given regular expression, you can actually have several equivalent evaluation plans. So if you have any word at ibm.com, you could evaluate it as any word at followed by IBM followed by dot followed by com, or you could do it the other way, look at IBM and so on. So which evaluation is planned depends on the selectivity of the posting list that you are processing for as entries in the regular expression. So we realize that, well, to look at equivalence, we need to look at properties of the operators constant and merge. So constant is associative but not commutative, whereas merge is associative as well as commutative, as you can imagine. So this is something that is a special privilege which database guys don't have. This is associative but not commutative, and because of this we are able to find optimal plans in some certain sense. So here's an example. So A followed by B or C plus DE. So there are two different plans, and the problem is basically to find the plan which will have the minimum cost, which will incur the minimum cost, and the cost is only sensitive to the ordering of consecutive intersection operations. We ignore merge here because solving this problem for merge operations is an NP-hard problem because merge is both associative and commutative. And we also need to use an estimate of the length of the intermediate posting list. So this rho is an estimator function, G is the particular graph, and I is the inverted index. So interestingly, in the interest of time, again I'll just highlight the problem is equivalent to that of finding an optimal parenthesization of matrix multiplication in a matrix chain. So and that's well, the number is very large, number of possible matrix chains, but it turns out that you can you have an order n cubed running time algorithm for this problem, and it is based on the central recurrence that the optimal sequence from I to j is the optimal sequence from I to k plus the optimal sequence from k plus 1 to j modulo the cost estimate for multiplying k with k plus 1. So there are also other, I'm skipping all results, but there are other interesting problems, like what if you have multiple plans and you want to optimize across all of them. So if you have R1 is A star B star C plus D, where plus is merge and star is the consecutive intersection or follows by. So now if you want to optimize across multiple such rules, plans for multiple rules, you might also want to consider a common sub expression. So this is again equivalent to finding optimal matrix chain multiplication across multiple matrix sequences. So here's an example. So you might consider a certain optimal plan for this, but what you realize is that there's a particular subtree which is common, A followed by B or C. So this part is common. So you might want to account for that. Unfortunately, the problem is NP hard, and you can show it by reducing from the smallest grammar problem. So but we came up with a bunch of heuristics and we built a scalable annotator framework. So we did a lot of work on how these rules can be induced also efficiently. So we talked about rules being provided to us, but how do you induce them? And it turns out that we can actually induce these rules, or a good starting point for the human annotator to look at by making use of these indices, index structures. So if we're talking about distributed machine learning, so where is learning? Well, inference is typically a part of learning. So all what we spoke about so far was inference, but any rule induction is going to require the inference technology that we talked about. So how much time do we have? Okay, so we looked at extracting these rules semi-automatically, And we made use of this index structure. Again, I'm going to skip this. So yeah, we could make use of the index structure, and our basic idea was look at instances in training data, cluster them, use this idea of divide and conquer, cluster them and generalize patterns from clusters. And this aspect of our work was tremendously made tremendously efficient by making use of the index structure. So this whole system was presented at EMNLP last year. We also looked at learning the candidate refinement rules. So just to recall, we had basic features and candidate definitions and candidate refinements. So we could actually learn these refinement rules optimally by using hierarchical kernels. Just presented a couple of venues. So I'll briefly go over the other two aspects, which is semi-supervised ontology population. And just to recall, what we talked about was information extraction with respect to the top level type system. So what about getting these nodes into the ontology, getting these leaf level nodes in? So this work has been looked at by several teams. In particular, the team at University of Washington, they built a system called Know It All some time back, and then there's a text runner. The idea is, given this ontology and relationships there, you're going to fire queries on existing search engines using patterns. So if you wanted instances of city, you'll say city is such as, and you look at snippets of text that return you comma separated values of proper nouns. However, these systems assume that you have access to an existing large index exposed through one of the standard search engines. The flip side is, however, that access to text data is only through the search engine, so you don't have access to the index themselves. So what we said is, well, if you want to enable the same on a corpus which is available to you, can you again make use of some smart features in the index and populate your ontology with nodes using the enriched index. So this is how we can populate nodes which are supposed to have instances from your enterprise corpus. So the idea is, in most of this work is, you look at pages that contain lists of your entity type instances. So here you're looking at instances of projects, team members and mentors, or another page you look at, sorry, the same thing is repeated here, names of staff and their email IDs and so on. You can look at pages which talk about profs and the courses they have taught, conferences and the name of the paper and so on. So this is the ontology population process we have. We enter a seed list or we enter some seed query which looks at our sophisticated index, which has all kinds of rich features, and we return a bunch of URLs. These URLs are ranked, and they are ranked based on the features we have. And the user can look at a page, look at the entries from that page that we are suggesting, and decide if he is happy with it. There's a checkbox here, he clicks on that and gives feedback to the system. So there's a keyword plus seed list query, keyword search results, and then the system ranks the potential pages potentially containing instances of the ontology nodes. There's a ranking model that gets constantly tuned based on the feedback that the user gives. So the model retraining happens based on relevance judgment when the user looks at the search results. And once the pages have been identified, once the user has zeroed down on the pages, again we look at both semi-automated and manual rule-based extractors to identify instances from those pages. So some of the features we use for ranking, okay, went out. So we found that visual features play a very important role in this process. Again, because we have access to the corpus, we can create our own index. We are able to identify all these the visual and lexical features and index them. There are a bunch of existing visual extraction, visual features that have been investigated in literature. But the important point to note is we are able to index all of them and speeding up the whole process. So here are some results which I can skip. The last problem we looked at, okay, so the problem of entity disambiguation was that of associating spans in text with leaf level nodes, and we realized that this requires a lot more scale up because we are not restricted to a small type system. There are lots of types, and also we need to exploit relationship between the entities that occur on a page. So basically there are several interesting issues here. So you might have a document here with certain potential spans or spots, as we call them. These spots could be associated with entities or might not be associated with any of the entity. It might be associated with more than one entities. So there are a bunch of issues that need to be tackled. The association with multiple entities is primarily because the context is not sufficiently disambiguating. And what kind of features can we use here? The feature construction is based on the document itself. The features can also come from outlink index, inlink index, and category index between the pages that Yago points to. We make use of a Markov random field to do the disambiguation, and we investigated two processes for collective disambiguation based on Markov random field. So what do you mean by collective? So here's a small snippet. This jaguar here could mean jaguar the car or jaguar the animal. And you could look at the overlap between jaguar, the car, and all the candidate labels. So this is just in some sense the spot based local context similarity. And this can be the features that you need for lookup can be very, very large. So we made again interesting use of indexing structures to make use of compression of the feature space and make the computation in reasonable time possible. There's also the aspect of collective disambiguation. So you need to collectively disambiguate some of these entities based on collective signals. This has been investigated using two different approaches. In the interest of time, I'm going to just present the summary and conclusions. So we looked at the potential I would say data structures for speeding up inference of entity extraction and disambiguation. And the relevance to learning, as I pointed out earlier, is that inference is generally a subroutine in learning tasks. And there are several questions for investigation with respect to this workshop, and I'll be happy to discuss them. So how about distributed computing for inference on text documents? How about distributed learning of features? And one thing that is of great importance to this project itself is how do you incorporate human interaction and distributed computing? So if you have these features and inferences going on in different nodes, how do you put a pause to the entire process and incorporate human feedback without resulting in too much latency? So these are some points that came to my mind. Thank you for your attention. Okay.
Questions? So far you have not done any experimentation with the distributed scale-up infrastructure.
No.
The runtimes that you're seeing in the sequential case for the 3 questions, how much do they range?
If you didn't make use of the index at all?
And if you did?
So in the first case, it is, as I said, it's an order of magnitude speed up. In the second case, it really depends on the density of the instances that you find in the target collection, because as you keep going down this ontology, the density is supposed to increase. So it's only expected that the order of magnitude speed up should grow.
But what are the constants here?
So the overheads in some sense, or
The actual numbers. Are you talking seconds, hours, minutes?
oh, okay. So the overall time. So overall time. Somehow we were restricted to use of existing corpora which are annotated, because we had to ensure that whatever rules or models, graphical models we came up with are consistent with existing annotations. So they were typically in a couple of GB. So that's all we could test on. And as I pointed out in some of those slides, it would range from a few minutes to a couple of hours, depending on the density of annotation.